Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. Hi there, welcome to part 5 of the mini course Preparing for Organic Chemistry. In this video lesson, I introduce you to the world of isomers in organic chemistry. So let's get started. Just to remind you where we are, we have completed our discussion of or introduction to Lewis electron dot representations. And again, this video is an introduction to isomers. So let's start with a flowchart. You've all seen flowcharts of biological taxonomy, right? Of course, flowcharts are a great way to organize information, especially nested information that has terms and definitions that are subordinate to higher terms and definitions. So again, for biology, we have at the very top all life forms on Earth. And then right below that, we have the kingdom of plants and the kingdom of animals and the kingdom of fungi and so on and so forth. Well, we're going to take a similar approach here to isomers in chemistry. So at the very top of this flow chart, we have all isomers. And keep in mind that when we refer to isomers, we're referring to a relationship between two or more molecules, right? You can't point to a compound and call it an isomer. That has no meaning. It's an isomer with respect to which other molecule or molecules, structure or structures. Now, all isomers at the very top share what? Well, they share identical molecular formulas, identical chemical compositions, right? The exact same type and number of atoms and elements that make up that molecular substance. But they differ in how those atoms are bonded and how they're connected and how they're bonded. Now, the first big split right after all isomers is the difference between constitutional isomers and stereoisomers. And let's just say for now, right, and you can see this very clearly on this slide, that there's a lot more to stereoisomers than there is to constitutional isomers. Let's get into this now. Now, I could give you a long formal definition of constitutional isomers and stereoisomers, and I'm not going to do that. Instead, what I'm going to do is give you a functional definition. And so what I want you to, and I'm going to give you examples in a moment here, but what I'm doing here is I am telling you what needs to be done, what actually has to be done to a molecular structure, right, to generate either a constitutional isomer of that structure or a stereoisomer of that structure in terms of making and breaking bonds. Now, no one's making and breaking bonds. We're not doing any chemical reactions. We're far from that in our mini course. Okay, we're just saying conceptually. So if two or more substances are constitutional isomers, they are constitutional isomers because to interconvert them, quote unquote, in theory, you have to make and break bonds to different atoms. Make and break bonds to different atoms, as opposed to stereoisomers, where to interconvert two or more stereoisomers for a stereoisomeric relationship or relationships, you have to make and break bonds to the same atoms. Now, I know this doesn't mean much to you now. It will mean more shortly. So just bear with me for now. All right. Again, the world of stereoisomers is much more complicated than the world of constitutional isomers. The split after stereoisomers is you either have chiral carbon stereoisomers or you have geometric stereoisomers. And geometric stereoisomers are fairly simple and they involve restricted bond rotation. And again, we'll see more about that in a moment. Chiral carbon is, I have to admit, a favorite topic of mine, but I'm just going to say that it is one of the most important and interesting topics in all of science. And it involves a very special circumstance when four different attachments are bonded to the same central tetrahedral atom, and it's generally carbon, but it can be other atoms like phosphorus or sulfur or silicon. But four different attachments, including a lone pair, when four different attachments are bonded to a central tetrahedral atom, that confers very special isomeric properties on that compound. And we call that phenomenon chirality. And there is another split after chirality. You can have absolute chirality or relative chirality. Absolute chirality can be had with only one chiral carbon, but it can exist with more. Relative chiral carbon stereochemistry, stereoisomerism, requires at least two chiral carbons. Now let's get into this in further detail and start to look at some examples. Let's first look at the difference between constitutional and stereoisomers. We said that for two or more substances to be categorized as constitutional isomers, their interconversion requires making and breaking bonds to different atoms, whereas to qualify as stereoisomers, their interconversion can be done by making and breaking bonds to the same atoms. So let's see what this actually means. So what you see on this slide are the series of saturated alkanes. Alkanes are a type of hydrocarbon, and of course hydrocarbons are organic compounds that are comprised only of hydrogen and carbon, and they're very, very important in energy, right? Gasoline, diesel fuel, home heating oil, jet fuel, crude oil, right? These are all, this is the very, very, very huge and important hydrocarbon industry, which we're trying to, right, reduce, because environmentally it has serious consequences. But anyway, this is the series of organic compounds known as saturated alkanes. And they all follow the formula CnH2n plus 2, where n goes from, n is an integer, 1, 2, 3, 4, so on and so forth. So for instance, the simplest saturated alkane in organic chemistry is methane, CH4. You can see it there, right? 1 carbon, 4 hydrogens, right? 2 times 1 is 2 plus 2 is 4, CH4. After that, we have ethane, C2H6, right? 2 times 2 is 4 plus 2 is 6, C2H6. So they all follow that formula. But what I've also listed here are their constitutional isomers. Now notice that for the first three of these, methane, ethane, and propane, there are no constitutional isomers, right? There's only one way to connect, say for propane, there's only one way to connect 3 carbons and 8 hydrogens, and that's it right there, right? To generate a valid Lewis electron dot structure, of course, is what we mean. And that's true, of course, for ethane and methane. But once we get to C4H10, once we get to butane, the 4-carbon alkane, there are 2 different butanes in the world, in the universe, right? You have what's called N-butane on the left, or normal butane, and you have what's called isobutane on the right, or isomeric butane. N-butane, isobutane. The N prefix in organic chemistry stands for normal, and it means fully extended straight chain, no branching. Fully extended straight chain, no branching. Notice in the isomer on the right, there is a branch point at carbon 2. That's called a branch point. Okay. Once we get to C5H12, right, we go from 2 constitutional isomers to now 3. Okay, and I will just tell you, and you can look this up for yourself, that as the formula increases even further to 6 carbons, 7 carbons, 10, 12, 40, so on and so forth, okay, the number of possible constitutional isomers, right, goes up very quickly, and it's not linear. It goes up very, very quickly, and we actually need computers to assist us in that analysis. But of course, we can handle C1 through C5 or even C1 through C6. And these are constitutional isomers, and how do we know that? We know they're constitutional isomers because in the case of butane, right, to interconvert the two structures, we have to break bonds on the left, the red dashed lines, and then move those atoms or groups, or really switch their positions and form new bonds on the right, the green lines. Break bonds on the left and make bonds on the right to different atoms. Right? So in other words, again, look at the left hand isomer and look at the methyl group, the CH3, the last carbon in that structure. We break the bond between carbon 3 and carbon 4. And we make the bond on the right between carbon 2. And what was carbon 4? We're making and breaking bonds to different atoms, constitutional isomers. I'll leave it up to you to convince yourself, and you should do this as an exercise, that the same must be done to interconvert the 3 pentane, C5H12, the 3 pentane constitutional isomers. The same analysis applies. I'll let you do that for yourself. Now, what about these structures? Now, this is the 6 carbon. These are the hexanes, right? C6H14. What about these 3 structures? Constitutional isomers? Some other type of isomers? What do you think? Take a look. No, it turns out that these are 3 identical molecules. They're simply different Lewis electron dot drawings or sketches of, right, the same molecule, which is N-hexane. And in the middle structure, right, I've kind of kinked the chain to make it sort of turn back on itself. In the third structure, I kind of have an intermediate kink in the chain and then straighten it out. But the point is the connectivity doesn't change. Constitutional isomerism and connectivity for the carbon framework, okay, that's not a coincidence, that's intentional. Okay, now these are just different Lewis electron dot drawings of the same molecule. They are not isomers, and you're going to have to develop the facility to know this, and your professor will try and trick you. I'll just tell you right now. They'll try and trick you into thinking that these are isomers when in fact they're the same molecules. Now we get into the world of isomers, or stereoisomerism. And I mentioned before in our flowchart, you saw for yourself, it's a much more complicated world. Let's first talk about the difference between geometric stereoisomerism and chiral stereoisomerism. Geometric stereoisomerism involves restricted rotation about a double bond. Period. That's it. Restricted rotation about a double bond. And so what you see at the top here in the left-hand panel, you see the two geometric 2 butenes, right? Bute, 4 carbon. You saw butane before, right? C4H10. This is C4H8, right? This is the alkene, not the alkane. Alkene being the carbon-carbon double bond. And because there's restricted rotation by the carbon-carbon double bond, and that's essential, because there's restricted rotation, okay, and you can figure out for yourself why there's restricted rotation about a carbon-carbon double bond and not a carbon-carbon single bond. Because there's restricted rotation, those configurations are locked, okay, and distinct. In other words, you can have a 2-butene molecule where the N-methyls are far apart, that's the left-hand structure, or you can have a 2-butene geometric stereoisomer where they're closer together, that's the right-hand structure. The left-hand structure we call the trans geometric stereoisomer, and the right-hand structure we call the cis. And you can see that it meets the definition of stereoisomers because if I used my red dash line, green line method, you can see that we have to break bonds on the left-hand structure, and then we make bonds on the right-hand structure to the same atom, right? We break the carbon methyl bond in the left-hand structure, and we reattach it to the same carbon atom, C3, on the right-hand structure, just in the different configuration. So that's why these still count as stereoisomers, but they're geometric stereoisomers, as opposed to chiral stereoisomers. Oh, what an important area that is. What a fascinating area that is, right? Get ready to be amazed, because chiral carbon, as I mentioned in the definition, involves, or a chiral atom, a tetrahedral atom, carbon in most cases, that is bonded to 4 different attachments. That's the requirement. And you can see I have an example here. I have a central carbon bonded to a hydrogen, a chlorine, an OH, and a methyl, hydroxyl and a methyl, okay? And notice something. The relationship between the left-hand structure and the right-hand structure is what? Yeah, they're mirror images. They're mirror images, but they're not identical. They are non-superimposable mirror images, just like your left hand and your right hand. Hold up your hands, hold up your left hand, and hold up your right hand, and hold them right out in front of you. You can see that they're mirror images of each other. Now try and superimpose one hand on top of the other, and you can't, because your right hand thumb goes to the left, and your left-hand thumb goes to the right. They're non-superimposable mirror images. And there's something very, very special in biology about that we'll get to another time. But you can see that this also meets the definition of stereoisomers, because to interconvert the two, I have to make and break bonds. In this case, I showed to the chlorine and the hydroxyl, but you could do it to any 2 attachments. I make and break bonds to the same central carbon atom. Stereoisomers. Finally, we have the distinction between absolute chirality and relative chirality. On this last slide, you see in the top left-hand panel what you saw before. Okay, now that's absolute stereoisomerism because it involves only one chiral carbon. If there's only one chiral carbon, okay, then the stereoisomerism must be what we call absolute. What if there's a second chiral carbon, like in the right-hand panel? Okay, I introduce a second chiral carbon. And what you see in the top part of the right-hand panel, you see the mirror image reflection of the original structure with the 2 chiral carbons. And I'll leave it to you to convince yourself, and you can use your models, and you should now begin to use your molecular models to understand these spatial aspects. That's very important. I'll leave it to you to satisfy yourself that these are non-superimposable mirror images. All right. And so they have that absolute stereochemical relationship. Okay, but what if instead of the upper right-hand panel, we have the lower right-hand panel? Now, what's the difference? The difference is the pair in the lower right are not mirror images. They're not mirror images because what I've done is I've changed the configuration of the second chiral carbon. Notice I've switched the OH with the H, but I haven't switched the original chiral carbon. There's a different internal relationship now within the molecule. There's a different internal relationship within the molecule, and we call this relative stereoisomerism. And I will just say one more thing about this. Absolute stereoisomers, and the other name for that is enantiomers, have identical properties in the lab. You can't tell them apart. Same melting point, same boiling point, same NMR, same infrared, same reactivity. So why do I indicate that they're not identical? Well, they're not identical when it comes to two and only two aspects of science. Number one, when you measure what's called their optical rotation, which is how these molecules interact with plane polarized light in an instrument called a polarimeter, one form rotates the plane of polarized light in one direction by x degrees, and the other form rotates it in the opposite direction by the same number of degrees, clockwise or counterclockwise, x degrees or n degrees. The other difference between two absolute stereoisomers or an enantiomeric pair, which you see in the upper left and in the upper right, the other difference is when these molecules encounter a chiral environment. What's a chiral environment? Our bodies are chiral environments, right? How come? Because all the receptors in our bodies are comprised of what? Proteins and carbohydrates, glycoproteins. All of these proteins and carbohydrates have chiral carbons, and they only have chiral carbons of a certain configuration. So much more about this later, okay? But you can't tell the difference between absolute stereoisomers in a lab unless you perform special experiments. There are ways of doing this, but in general, you can't tell the difference. Now, when it comes to relative stereoisomers, different melting point, different boiling point, different spectra, different reactivity, maybe related reactivity, but different. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.